EOI 2267b is listed, I know it's quite a mouthful in terms of the name, is listed as a potential habitable exoplanet. So it's under the classification of terrestrial, meaning rocky formation. It's not a gas giant. Its orbital period, which is essentially, could be understood as the time it takes to make one complete orbit around its star. So for example, Earth's orbital period is 365 days, 1 year, to go all the way around our sun. That's essentially what the orbital period is. This planet's orbital period is 2.3 days, and its radial distance is 0.0205 astronomical units. Mouthful. We're going to talk about what is the mass of the star it orbits, and we're going to answer in solar masses. So the thing we are looking for is we're looking for the mass of the star. I'll call MS. This is a mass of the star it's orbiting. And let's draw an image. I'm going to draw the image right up here. I'm out of the way. So here will be our little star. And it's at a radial distance away. Here's the exoplanet. The tangential velocity is going to have it orbiting in a circle. And that's kind of essentially what we are. Again, I count for it. It doesn't need to be much more detailed than that. All right, so what are the values or numbers I'm given? I'm going to convert these, but the radial distance, R, is 0.0205 astronomical units. I'm going to convert that to meters. And the reason I need to do that is when I use Newton's gravitational force equation, the gravitational constant G has units of meters in there, so I do need to convert it. I'm going to get rid of, there's for every one astronomical unit. Again, astronomical unit is defined as Earth's distance to the sun. It is 1.496 times 10 to the 11 meters. And the reason we kind of put these in terms of astronomical units is because space is really big. So it gives us something to compare it to when we use that. But if I plug this in my calculator, I get 3.067 times 10 to the 9 meters. So it's significantly closer to its star. And then our orbital period, that's I'm going to call T. We're going to use this to figure out how fast the star is going. Right? If I know it has to make one complete circle and I know the radius of that circle, I can kind of use this idea of circumference to essentially figure out how fast the star is going, which is going to help me with respect to what we're looking at for this. So really help me in terms of the centripetal acceleration equation. But so the time I'm going to write out as 2.3 days. I want to convert to seconds. So for every 1 day, there are 24 hours. And for every 1 hour, there are 3,600 seconds. If you didn't know that, you could convert to hours to minutes and then to seconds, but you get to the same result. When I plug this in my calculator, I get 198,720. So 198,720 seconds. And these are the two numbers I'm going to use with respect to how I'm going to evaluate this. That's pretty much the only bit of information I'm given, though. I'm not really given anything else. So the equations I'm going to use three equations. I'm going to use the gravitational force equation, Fg. That's equal to G, big M, little m, over R squared. I'm going to use the centripetal force equation, because that's essentially what I'm going to set it equal to. That's equal to the mass times the centripetal acceleration. Another way, though, I can expand centripetal acceleration or centripetal force is that it's the mass, the angular velocity squared times the radius. So that's actually the one I'm going to use. So omega is this angular velocity, where omega is going to be the change in my degree rotation. In this case, it's 2 pi over a time period. So for what we're going to be using, it's going to be 2 pi over our time, which we just calculated what our time is. That's the thing we're reviewing. All right, so our solution set, I'm going to start by setting the centripetal acceleration equal to the gravitational acceleration. This is going to look like I'm going to use this format already, just with omega. The mass, omega squared times the radius. And this is little m. Since it's the planet that's orbiting, it's the mass of the planet. This is going to equal the gravitational constant. Big M, I'm going to put the little subscript for S for the star. That's the thing we want to figure out. Little m, that's again the mass of the planet divided by their radial distance squared. You'll note it doesn't actually matter what the mass of the planet is, which is good because I don't give it to you. So it doesn't actually matter what the mass of this planet is because how close it is to the star. It's going to affect its orbital period and radial distance. I'm going to expand what I have kind of rewritten omega to be, right? I know if it makes one whole circle in 2.3 days, I can kind of from that calculate how far it's going to go. In terms of its one whole circular rotation, that's 2 pi. And you can kind of see where this is coming from. 2 pi r is the circumference of a circle. So in this case, I'm going to have let's expand that a little bit more. 2 pi over t, that's my omega. That is squared times the radius, so just right there. And that's going to equal gravitational constant, the mass of the star divided by the radial distance squared. These radius components, they're the exact same thing. They both mean radial distance. So I'm going to multiply r squared to the other side, and I'm going to divide gravitational constant. So I get that the mass of the star is equal to, we're going to have radius cubed divided by, I'm just going to put g right down there. And then I'm going to distribute this square just to simplify some of my math. That's going to be 4 pi squared divided by t squared. And all of these are things I know. I can go ahead and plug in my numbers. The radius squared is going to be this big number. So we want to be careful with our operation when we plug this into the calculator. But it's 3.067 times 10 to the 9 meters. That is cubed over gravitational constant is 6.67 times 10 to the negative 11. I'm going to write out the units for this. The units do matter. It's Newton meter squared per kilogram squared. I have 4 pi squared divided by the time squared. So that's going to be 198,720 seconds. That is also squared. When I plug this into my calculator, I get 4.316 times 10 to the 29 kilograms. And I have one more final step to do. I have to convert it. If we remember, we wanted our answer in solar masses. So we're going to compare this to solar mass. I'm going to write down what I have. 4.316 times 10 to the 29 kilograms. And I have kilograms down here. That's the unit I want to get it rid of for everyone. Solar mass, I have 1.989 times 10 to the 30 kilograms. That's the mass of our sun, hence solar mass. So that's where the term comes from. When I plug this in, I get 0.217 solar masses. So it's about 20% the size of our sun. So it's quite a significantly smaller star, which makes sense if the planet's a lot closer, right? If we were that close to our star, we'd be like Mercury, we'd be burnt to a crisp. But that's because our star's quite a bit bigger, significantly more powerful, significantly hotter. This would be a smaller star. It's okay that the planet is a lot closer.